Hello everyone, welcome to Analog Electronic Circuits, lecture number 16, part number 2. So today we are going to solve a numerical on a Cascade amplifier. So let us start. So a two-stage RC coupled amplifier have JFET parameters as IDSS equal to 7 milliamperes, VP is equal to minus 2.5 volt, RO is equal to 50 kilo ohms. And the here instead of MOSFET we have there is an error, there is a BJT, these are BJT parameters. So over here we have to write the BJT parameters are beta equal to 220 and VB is equal to zero point 0.7. Now if they don't give it a value of RO, we have to assume the value of RO as infinite. Okay, so that's the assumption. So always remember, if they don't mention the value of RO, we have to assume it to be infinite. Now what do we need to calculate? We need to calculate input resistance Rin, output resistance R out, and the output voltage V out for the circuit given below. So let us have a look at it. So this is the circuit given to us. So as you can see, the first stage is a JFET amplifier, self-bias. It's a self-bias JFET amplifier, and the second stage is a common emitter amplifier, right? So it's a common source, common emitter, cascade amplifier. Here we don't have a RSig, internal resistance is not there, neither we have the load resistance, right? So let us directly start. So first point is that due to RC coupling, the DC analysis of both the stages are isolated. That means we can independently calculate the DC Q point of the first stage and the second stage. So let us exactly do that and start with the DC analysis for JFET. Right. So first of all, let me write it down. So second point is DC analysis for JFET. Okay. Now, what is the criteria for a DC analysis? For DC analysis, all the capacitors will behave as an open circuit. So what we left out in our network for the first stage will be RG, RS, RD, and Q1. So let us draw that again quickly. Yeah. So we have the following circuit available to us now. This is RG, that's RD, and RS. Only this much is a network, and this is VDD. This is RD, and this is RS. By the way, we should always know what is the DC and the AC quantities in the circuit. So AC, we have small signal AC. At the output also we have AC V out, and that is a DC supply used to bias the transistors in the proper operating region. Okay, so DC, AC, and AC. Now let's come back to the circuit. So over here, let me mark the terminals now. This is the gate terminal, this is the drain terminal, and the source terminal, right? And here the current ID will flow through the resistor RD and also through IS, because the same current, also through RS, because the same current will flow through the drain terminal and come out of the source terminal, right? It's the same current. Now, what do you observe for the self bias configuration? Here the gate current is zero. Okay, so the gate current which is flowing is zero. So what will be the voltage VG over here? The voltage VG over here will be 0 volt. Fine. And now what is the voltage VS? So from here, your voltage VS, you can take it out, and VS can be written as IS into, or we can write it as ID. ID and IS are same. So we can write it as VS is equal to ID times RS. Okay. So let us write it over here. ID times RS. Now, how can we write VGS? So VGS can be written as VG minus VS. So that will be equal to VG is 0. So VGS will be equal to minus ID into RS. And what's the value of RS given to us? RS value is given as 720. Let us have a look at it once. So it will be minus 720 times ID. And this is our equation number 1. But we require to find the value of VGS and ID. We have two unknowns and one equation. So we'll require one more equation to solve this two unknowns, right? So let us check out the values. The value of Rg is 2.2 mega ohm, RD is 4.7 kilo ohms, RS is 720 ohm, CC1 is 10 microfarad, CC2 is 10, and CC3 is also 10 microfarad. CS and CE is 100 microfarad, R1 is 22 kilo ohm, R2 is 2.2 kilo ohm, RC is 1 kilo ohm, and RE is 330 ohm. And your input supply, your input voltage over here is 20 millivolt peak to peak. Okay, and the DC power supply is 24 volt. So these are the values of various resistors and capacitors in the network. So hence RS is 720. Now we'll assume that the second point over here, this is the first point. Second will be, we need to assume that the given JFET, assume that JFET is in saturation, is operating in the saturation mode. Okay, so therefore we can write the drain current as, as follows. So let me write it down. ID will be equal to IDSS into 1 minus VGS upon VP the whole square. Okay, now let me check it out. This IDSS value is around 7 milliampere, right? VGS we need to find, and VP value is around minus 2.5, right? So how do we write this expression again? So ID will be equal to 7 into 10 raised to minus 3 into 1 minus this VGS will come, and here you will have minus 2.5, so this will become plus. Okay, so that is the expression which we get. We call this equation as equation number 2. Now we see, compare the equation number 1 and 2. There are two unknowns, VGS and ID, and there are two equations. We can solve them simultaneously. So what do? Is we normally substitute the value of ID obtained in equation number 2 in 1. So whatever value we have got over here, we substitute in equation number 1. So what do we write over here? That's the third point. So put equation 2 in 1. So by putting equation number 2 in 1, we get, let me go a little down. So what is equation number 1? Let us see. It is VGS equal to 720 times minus 720 times ID. So we'll write VGS is equal to minus 720 times ID, means 720 into this equation number 2. So 720 into 7 milliamperes, if you calculate, it is 504. Okay, 5.04. 5.04, and inside you have this 1 plus VGS upon 2.5 the whole square, right? So let me evaluate that. Let me open the bracket. A plus B the whole square, that will be 1 plus 2 upon 2.5 into VGS, that will be 0.8 times VGS, and 1 upon 2.5 square, that will be 0.16 VGS square. Okay, so we got the quadratic equation in VGS. Let us quickly complete it. So that will be, these are straightforward steps, no explanation is required over here. We'll open the bracket, minus 5.04 plus 0.8 into 5.04 is here it will be minus, actually minus 4.032 VGS, and here again there will be a minus. 0.16 into 5.04 will be 0.8064 VGS square. You all can check it out very patiently and calmly, do this. And now we finally write the expression. We rearrange the terms, we'll get 0.8064 VGS square, and this we took it that side on the left hand side, and this, if you also took it on the left hand side, it will be plus 5.032 VGS, and again there will be a plus 5.04 equal to 0. So we have to solve this equation now quadratically. So we'll write over here solving quadratically. Okay, So solving quadratically, what do we get? You will get two values of VGS if you put it in the calculator and solve it. So the two values of VGS which are coming are, um, one value is coming as minus 1.2533, okay, or the next value is coming as VGS is equal to minus 4.98. So now we have to decide between which is the correct value, right? Now I think this one is the correct value, and why we have to write the reason also, since your VGSQ should be greater than VP. And what is VP? VP is minus 2.5. So minus 1.25 is greater than minus 2.5. So therefore, this value is correct, and we should reject this value. Okay, reject it. Fine. So finally, a value of VGS will be minus 1.2533 volt. Okay. So let me write it over here. So VGSQ will be minus 1.2533 volt. Fine. So let me highlight it with yellow color. Yeah. So now that we got the value of VGS, we can calculate the value of small signal parameters, that is GM1, right? Why we are calling it GM1? Because this is the first stage, right? So second stage will also have a GM. So to distinguish first stage from the second stage, we'll call it as GM1, internal parameter. And also we call this value RO, which is defined as RO, which is 50 kilo ohm, as RO1, because 1 stands for first stage, right? So let me continue with the analysis. So this is point number 4. So we'll first calculate GM. What is the GM formula? It is mod of twice IDSS divided by VP into 1 minus VGSQ divided by VP. Now over here, all the values are available. IDSS is 7 milliamperes. VP is minus 2.5. It's a mod, so it will become plus. VGS is minus 1.2533 and VP value is minus 2.5. So if you calculate in your calculators, put the values into calculator, you should get the value of GM1 as 2.793 milliampere per volt. Okay, and let me highlight this value. So we got the value of GM1, which will be helpful in calculation of voltage gain later on. Okay, fine. Now let me proceed forward and write down the value of RO1. Sorry. So fifth RO1, which is given value, it as RO, which is 50 kilo ohm. So we need not calculate anything because RO is given to us. We call it RO1 because it's a first stage. Fine. So we calculated the value of GM1 and RO1 and also the DCQ point, right? Now moving on to the next stage, I mean the third point, I guess. Let me check it out. So first we did the DC analysis for JFET. Now next we'll do the DC analysis for BJT. So let me write the third one. Yeah. So let me start. So third will be DC analysis. This time the second stage BJT. Okay. So let me quickly draw the the DC bias circuit. Okay. So it's looking like this. So we have BJT, NPN BJT. We have resistors R1, R2, RC, and RE. Fine. And here is the DC supply VDD. Here it is connected. This is, I think, R1, R2, RC, and RE. Right. And let me rewrite this. This is the base, collector, and emitter. We know what to do. We will convert this into Thevenin's equivalent. So we'll apply the Thevenin's theorem at the base terminal. And finally, what do we get? We get the following circuit now. So here we'll have VTH, RTH. This will be RTH. This will be VTH. And this we have done many times, so I'm not going in details. You all can check the previous lectures. This will be VDD, RC, RE, right? This will be plus minus VBE. Yeah? So this is the base terminal, the collector, and the emitter after application of Thevenin's theorem at the base terminal, right? So we have to calculate the value of RTH, VTH, IBQ, and then henceforth ICQ. So let me begin. Again, I'll write the first point over here. So first we'll calculate VTH. So what is the formula for VTH? VTH is R2 divided by R1 plus R2 into VDD, right? So what are the different values over here? So R2 value is 2.2K and R1 value is 22K. And VDD value is how much? 24 volt. Fine. So if you substitute these values in your calculator, you will get the value of VTH as 2.18 volt. Okay. Let me rewrite the 2 over here. So 2.18 volt. Highlight it with yellow color. Okay. Next, we will calculate the value of RTH. So RTH is nothing but R1 parallel to R2, and R1 is around, we have said just now, 22 kilo ohm, and R2 is 2.2 kilo ohm. So therefore, if you calculate in your calculator, your R1 parallel to R2 will come out to be 2 kilo ohm. Okay, so that's the value of RTH we get. Now we'll finally apply the KVL at the input loop and we'll find the value of IBQ, right? We have done that. I'm directly writing the expression now. Before, we have done many times the voltage divider biasing. So the value of the base current IBQ will be given by VTH minus VBE upon RTH plus 1 plus beta times RE. Correct? So now the values of VB is 0.7 volt. VTH we calculated it's 2.18 volt. RTH is 2 kilo ohm. I think beta value is 220, right? So this fraction will be 221 and RE value is how much? It's 330 ohm, right? So if you substitute all the values in your calculator, your value of IBQ will be coming out to be, what was the value? 19.75 microamperes. It's the value is 19.75 microamperes. Okay. And now it's pretty easy to calculate the value of ICQ. So ICQ will be beta times IBQ, right? Where the beta value is around 220. Yeah, it's 220 and the value of IBQ just now we calculated 19.75 micro. So multiplication of this will give you the value of ICQ as 4.345 milliamperes. Kindly cross check the value, and if you get any different value than this, please write in the comment section so that we can also improve that. Okay. Next is, why do we calculate the ICQ value? So that we can calculate the small signal parameters like GM. Now here in this case, the BJT is the second stage, so we'll calculate, call this as GM2. And what is the formula? Formula is ICQ upon VT, right? Where VT value should be known to you by now. It's a thermal equivalent of voltage. It is 26 millivolt. And ICQ, we just now got it as 4.345 milliamperes. So finally, you will get the value of GM1, which is close to 167.11 milliampere per volt. Okay, so that's the value of GM1 we got over here right now, and we'll use this GM1 value while we calculate the voltage gain. Okay, so let's proceed forward. Another small signal parameter for a BJT will be R pi. right? So what's the formula for R pi? The formula is beta Vt divided by ICQ, correct? So Vt value is 26 millivolt. That is, we have already established that it is 26 millivolt. ICQ value is 4.345 milli, right? And beta value is 220. So if you plug in all the values in your calculator, you will get, okay, so you'll get the value of R pi equal to 1.32 kilo ohm. Okay, let me highlight this value. Okay, so we got the value of GM1 R pi, and what about RO2 now? So RO2 is not given, so we'll assume it to be infinity. Okay, RO value is not given for BJT, so RO2 will be infinity. That is what we have assumed. Okay, so finally we got the small signal parameter values for both the BJT. I mean, we calculated the DCQ point and finally DC parameters. And now we calculated the small signal parameters for both BJT and JFET. So now is the time to calculate the voltage gain, right? So this is the third part. Earlier one we have the second part. We calculate the DC analysis. From the DC analysis, we calculated the the VGSQ, and from that we calculated GM1, right? RO1 was given to us. Then we did the DC analysis for BJT, and we calculated the value of ICQ. Hence, we calculated the value of GM2 and R pi, right? Now, what we will do is we will be calculating the voltage gain, R in and R out. That is what we require, and hence we will calculate the value of V out. So, to calculate the value of voltage gain, we need to draw the mid frequency small signal equivalent circuit. Fine. So, we'll start over here itself. We'll leave some space and we'll write point number 5, right? So, we call this as mid frequency. We have drawn this many times. For mid frequency, we'll consider all the connected capacitors as short circuit. So mid frequency, small signal equivalent circuit. So we'll quickly draw it and evaluate the formula. No need to derive it. Within one step, we can easily write down the formula just by observation. Okay, fine. So first of all, very quickly, we have to draw the small signal model for JFET and BJT, right? Before that, we will identify the terminals. This is my gate, drain, and source. This is my base, collector, and emitter for Q1 and Q2. Let's first draw the model for Q1 and Q2, and then we'll move on to the next point. Okay, so Q1 is a JFET. So for a JFET, we have the gate terminal, and then we have, let me just draw it a little this side. We have the gate terminal, we have the drain terminal, and then we have the source terminal. So over here between the gate, this is the gate, this is the drain, and that's the source. So between the gate and the source, we just have VGS, and between the drain and the source, we will have GM1 into VGS, right? And also we have RO1. RO1 was given to us. So this is the model for the JFET. And now for the BJT. For BJT, we have base, collector, and emitter, right? That's the base terminal, collector terminal, and emitter terminal. So in a BJT, between base and emitter, we have R pi. So here is my R pi. Voltage across this is V pi. And between collector and emitter, we'll have a current source, voltage dependent current source. Its value is GM2 into V pi, right? And we don't have RO2 because RO2 value is not given. We assume it to be infinity. So any infinity value of resistance is an open circuit, right? Now that we have drawn the small signal model for both BJT and JFET, now we'll connect the terminals together. So from the gate, we will have a resistor RG going to the ground. Then we have in parallel voltage V in. because for the mid frequency, all the connected capacitors will act as a short circuit. So let me draw RG over here. We'll have a resistor RG going to the ground, and then in parallel we will have V in voltage source. So here we'll have V in plus minus V in. This is RG. Now let us check at the source terminal what is to be connected. So at the source terminal, we have a capacitor and a resistor in parallel. So capacitor will be connected as short circuit. So source terminal will be connected to the ground. So let me connect the source terminal to the ground. So your source terminal is connected to the ground. Now let us check the connections for the drain and the base terminal. So let me again go back to the circuit. So drain and the base terminal are connected together with a wire because capacitor is a short circuit. Then from the drain terminal, we have a resistor RD. And from the base terminal, we have a resistor R1 parallel to R2 because VDD is grounded. The DC source is also grounded for AC analysis, right? So let me draw that. First of all, let me connect the drain and the base terminal. So here we have resistor RD. This is resistor RD. And here we will have resistor R1 parallel to R2. R1 parallel to R2. Then let's check the connection at the emitter terminal. So emitter terminal, if you see over here, we have a resistor in parallel with a capacitor. Since capacitor is a short, emitter terminal will be grounded. So let me go back over here and ground the emitter terminal. Yeah, emitter terminal is grounded. Now only collector terminal is left. So let us go back to the circuit diagram. So from the collector terminal, you have a resistor RC going to the ground because VDD is grounded, and that is connected to the output, right? So we just have a single resistor RC connected over here. So this is RC, and in parallel we will have voltage V out. Okay, so this is the small mid frequency small signal equivalent circuit with which we have to calculate R in, R out, and the voltage gain, right? So first let us directly calculate the value of R in, right? So let me write over here first R in. Now could you help me out in calculating the value of R in? So R in a cascade amplifier will be equal to R in of the first stage. So here over here, this is my R in. So what do you see over here? You see resistor RG, right? And you have an open circuit. So R in will be equal to R in of first stage, right? And that is equal to RG only in this case, right? And what's the value of RG given? The value of RG is given as 2.2 mega ohm. No calculation required. We just have to write this. Rin is equal to Rg, and that value is 2.2 mega ohm. Correct? Now let's calculate the R out, that is output resistance. So let me add over here. This is R out. So R out, output resistance, the cascade amplifier will be the R out of the last stage. In this case, it is the second stage. So meaning if we, let me go over here. Yeah. So from here, if you sit here and look on the left hand side, this is R out. What do you see over here? So you see register RC. There is no RL, there is no RO2, right? You just see it's a register RC. So that means your R out is nothing but this is equal to RC itself. And what's the value of RC? The value of RC, I think it's 1 kilo. So that's the value of your output resistance. So output resistance value is 1 kilo ohm and the input resistance value is 2.2. As you can clearly see with numbers, in a common source, common emitter amplifier, the input resistance of the amplifier is, of the cascaded amplifier is much higher, right? And the second stage being the BJT, its input resistance is much lower compared to the first stage. Now let us concentrate and calculate the voltage gain. Okay, so the third component over here is the voltage gain. So voltage gain, which is V out upon V in. So let us calculate the individual stage voltage gain. So here we have V out. So the output of the first stage, let me call it as, let me use a different color. Let me call it as V1. V1 is the output of the first stage and the input of the second stage. So what is my gain of the second stage? V out upon V1. And what is my gain of the first stage? V1 upon V in. So this AV, which is the overall voltage gain, can be written as V out upon V1 into V1 upon V in. Now V out upon V1 is nothing but my gain of the second stage, which is AV2, and V1 upon V in is nothing but the gain of the first stage, AV1, right? All right. So let's proceed now further. We need to quickly calculate AV1 and AV2, which we can easily do it over here. So let me write it very quickly with using green color. So now what is V out? V out is nothing but this current, which is outgoing current over here. It will be minus because it's not going to the ground. So this will be the current GM2 into V pi. This current into resistance RC. And what is V pi? V pi is in parallel with, it's the same as V1. So instead of, V pi, we'll use V1, right? So, sorry. So your V pi is equal to V1. So what will be my, voltage gain V out upon V1? Your AV2, which is V out upon V1, will be minus GM2 into RC, right? So that's the formula. We'll be using this formula to calculate the voltage gain of the second stage. Now let's come back to the first stage. So for first stage, what is the value of V1? Similarly, V1 will be this current, which is GM into VGS, current source, right? Outgoing current source, not flowing to the ground. So it will be minus current. Why minus? I've already told you all, it's not flowing to the ground, into these resistances in parallel. So what are the resistances in parallel? RO1 parallel to RD, parallel to R1, parallel to R2, and parallel to R pi. So these many resistances in parallel. And then what is VGS? VGS is same as V in. So VGS is equal to V in, right? So what is the voltage gain now? V1 upon V in. It will be minus GM1 into RO1 parallel to RD, parallel to R1, parallel to R2, parallel to R pi, right? So we got the formula for AV1 and AV2. Now let me write it formally over here. So AV2 will be given by, we have earlier calculated AV2, it is minus GM2 into RC. So what was the value of GM2 we got? We got it as 167.11 milliampere per volt. And what's the value of RC we got? RC we have 1 kilo ohm. So the voltage gain over here will be AV2 will be equal to minus 167.11. So voltage gain for the second stage, which is a BJT, will be greater than 100. Here it is showing that. And next stage will be, we will calculate the gain of the first stage. So far we have written the formula for V1, right? V1 expression. So V1, if we substitute V in over here, and V1 upon V in will be minus GM1 into these 5 resistances in parallel. So we can directly write AV2, AV1. AV1 will be minus GM1 into those 5 resistances in parallel, which is RO1 parallel to RD, parallel to R1, parallel to R2, and parallel to R pi, right? So let us find out what are the values of all these quantities. So first value is GM1. GM1 is around, how much is GM1? Let me check it out once. Yeah, GM1 is around 2.793 milli, right? So that's the value of GM1. And next, let us calculate RO1. I mean, RO1 is given as 50 kilo ohm. RD value is 4.7 kilo ohm. R1 value is, I think R1 and R2 we have calculated before. So R1 parallel to R2 is 2 kilo ohm, correct? And the value of R pi is coming out to be 1.32 kilo ohm. So all these things we have calculated. R pi we calculated, GM1 we also calculated. So we have to multiply this, do this evaluations, do this calculations in the calculator. So there will be 50 kilo ohm parallel to 4.7 kilo ohm, parallel to 2 kilo ohm, parallel to 1.32. So obviously the result will be lesser than 1.32 kilo ohm, right? That multiplied by 2.793 milliampere per volt, and you will get the value of AV1 as minus 1.874. So that's the value of AV1 which we'll get, minus 1.874. So that's the voltage gain of the second stage. Now to calculate the overall voltage gain, so let me do that. So AV total will be AV1 into AV2. So AV1 value we just now got, and AV2 value was minus 167.11, right? AV1 value is minus 1.874. So finally, the overall voltage gain is coming out to be, if you multiply these two quantities, it will be 313.16. So that's the value of overall voltage gain for the given cascade amplifier. Now we have to calculate the output voltage, right? So to calculate the output voltage, we'll write the total formula. V overall voltage gain formula. It is V out upon V in. So to calculate V out, it will be V in into AVT. So what's the value of V in given? V in is given as 20 millivolt peak to peak, and AVT is 313.16. So if you multiply them together, the value of V out, which will come out to be, it will be 6.26 volt. Okay, so that's the value of the output voltage which we were looking for. And with this, we have completed the numerical on this given cascade amplifier. Fine. So we have come to the end. We have evaluated the value of V out. We evaluated the value of total voltage gain, individual stage voltage gain, and we also found out the value of Rn, which was 2.2 mega ohm, and R out, which was 1 kilo ohm. And that is what was asked in the numerical, to calculate Rn, which we already completed. So we calculated the value of Rn, R out, and the output voltage. So with this, we come to the end of this session. So next time we will start with BJT based cascade amplifier. So until then, have a good day and thank you.